Alright guys, we're going to take a look at a few more examples in the notes just to help us get a little bit more comfortable with this limit by hand process where we're trying to figure out the value of a limit. We filled out the flow chart the other day in class. We looked at a few more examples together in class, but I just want to make sure today for your assignment we can take a look at a few more examples. And again, if you need help, okay, please try to get in contact with me and we can kind of iron out any difficulties you might have. So we're going to go ahead and take a look at G because I'm pretty sure we skipped that one when we were together the other day. And the reason I wanted to skip it is because if we were to try to plug in 3 over 2, okay, for those x's, I believe we would get 0 over 0. Okay, you can take the time to check that yourself if you want to. So this is kind of signifying a hole that we have in the graph at the spot of 3 over 2. But that's also telling us that the limit should exist because from the left and the right of a hole, they're approaching the same y value. So there should be something else we can do to this equation to eventually figure out that limit value, okay, the height of the hole. And in order to do that, if we think about some of our algebra techniques, we're not necessarily going to use a conjugate because we're not dealing with a square root, but we are going to try to factor. And what's different about this one is the numerator is an example of perfect cubes. I know we've talked about the perfect square factoring technique, okay, the difference of perfect squares, but notice how here we're dealing with perfect cubes. So at the top of the page, I kind of wrote down the factoring technique for these perfect cubes. Notice how you can either be adding them together or subtracting. That's what's a little bit different than the perfect squares technique, because in that case you have to be subtracting them. But we're going to go ahead and see kind of how these can be used. So if we think about the perfect cube of 8, that would be 2, because 2 times 2 times 2 is 8. And then the perfect cube of x cubed is x. The perfect cube of 27 is 3. Okay, 3 times 3 times 3 is 27. So this 2x is kind of acting as your a variable, and this 3 is kind of acting as your b variable. Now, in this example, notice how we're subtracting them together, so we're most likely going to use this setup. So in order to write our factors, notice how our first factor is a minus b, so that we can do 2x minus 3. And the other factor is a squared. So if I did 2x times 2x, that would be 4x squared. I then need to add ab, so 2x times 3 would be 6x. And then I need to add b squared, so 3 squared would be 9. Okay, so we can use either of these setups for perfect cubes. This is definitely not a common example. Okay, perfect cubes don't really show up that often, but I did want to just take a time to go over an example in case they do. Please excuse the bell. Okay, so on the bottom we have the 2x minus 3. So notice how these can now cancel. We're left with 4x squared plus 6x plus 9, which is a simplified form of the fraction that we started with. So even though 3 over 2 did not initially work when we plugged it in because we got 0 over 0, if we tried to plug in 3 over 2 now, okay, in for the x's, and you can go ahead and take the time to try it, but I believe you would get 27. All right, so there's our limit value. We went over h in class. So let's go ahead and check out letter I. Always try direct substitution first. It seems like, unfortunately, if I go ahead and plug in 1, I'm going to get 0 for the top and 0 for the bottom. So it looks like we do have another hole. Okay, so that means we should anticipate an answer. We just have to rewrite this in order to help us get that answer. So notice how we're dealing with a square root. We'll go ahead and utilize that conjugate concept. So that would look like 1 plus the square root of 2x squared minus 1. And we're going to multiply that on the bottom as well. All right, so let's go ahead and multiply the tops together. When we go through the FOIL process, since we're using conjugates, the outside and inside is not going to be necessary because we kind of already discussed how those are going to cancel each other out. So I'm just going to multiply the first together. 1 times 1 is 1. And then I'm going to multiply the last terms together. So I have a negative square root times a positive square root. So we know that's going to be negative. And since they are the same square root being multiplied together, we know that we're just going to be left with the inside part. But we kind of have to be careful to put that in parentheses. Now on the bottom, since these are not conjugate pieces, that means I'm going to try to that means I'm going to keep them separate. Okay, I'm not even going to bother multiplying them together. So let's see where this can take us. We'll go ahead and distribute in the negative sign. All right, and it seems like we can combine some like terms up top. Negative 2x plus 2. All right, now if we think about it, I know it's a lot of work from here, but remember, since we got 0 over 0, we know there's a hole at 1. We should be anticipating something to cancel out to show that removable idea. So if you take a look at what we have here, maybe we can factor the top and take out a negative 2. So we'll be left with x squared minus 1. And after you notice that, hopefully we can kind of see how this is a difference of squares that we can factor even further. So that would be x plus 1 and x minus 1. All right. So looking at what we have here, the x minus 1s can go away. So we're left with 2 times x plus 1 up top, and then this conjugate piece on the bottom. And thankfully, okay, since something removed, then this must be kind of the simplified form that we have left. So let's go ahead and take the time to plug in 1 and see what we get. If I plug in 1 up top, negative 2 times 2 is negative 4. If I plug in 1 on the bottom, 1 plus 1 would be 2. So it looks like I get negative 2. All right, so there's my limit value. All right, let's take a look at J. Okay, fractions galore, but again, we want to try to do substitution first. So if I plug in 0, I'll get 1 over 2 plus 1 over 0 over 0. Now, unfortunately, we can't really go much further because we have this undefined value, but really the whole fraction is undefined because we have a 0 in this denominator. So since we can't go much further from here, are we really able to say which undefined setup it is? Do we know for sure it's 0 over 0? Do we know for sure it's a number over 0? Okay, I don't know if we can make that decision just yet. So because of that, we're going to try to rewrite this or simplify it a little bit more so that we can get one of these two results that we're kind of familiar with or we've seen already. So let's think about some fractions. Notice how in the numerator we're adding fractions together. So if you think about some fraction properties, that means we have to have a common denominator. So in order to do that, I'm going to take this denominator of x, and multiply it on top and bottom of this other fraction. So I'll go ahead and write that. To get a common denominator for this second fraction, I'm going to take the denominator of x plus 2 and multiply it on top and bottom. And now you can see how the denominators are exactly the same. Okay, they're common. So now that we have a common denominator, we can go ahead and add the tops. So x plus x is 2x, and then we have that plus 2. So then we can keep the common denominator, and that's still all over x. All right, so where we can go from here is instead of dividing by a number or a variable, we can think about multiplying by its reciprocal. So I'll go ahead and multiply by 1 over x. And by doing that, I'll get x plus 2 divided by, let's see, x times x would be x squared, and then the x plus 2 on the bottom. All right, so we were using some fraction properties. Instead of having numerous fractions in one function, notice how we can simplify or reduce it to just one fraction. So now let's go ahead and plug in 0 to see what exactly we're dealing with here. All right, so if I plug in 0, I'll get 2 up top. And if I plug in 0 on the bottom, 0 times 2 is going to be 0. All right, so now we know for sure that we're dealing with this concept of a number over 0, which is signifying a vertical asymptote at this location of 0. So this is when we got to ask ourselves, okay, according to that flow chart that we filled out, is this an overall limit that we're dealing with, or is it a one-sided limit? Okay, and clearly we don't have that plus or minus going on, so this is an overall limit. And an overall limit does not exist at a vertical asymptote. Never, ever. All right, so we'll go ahead and say does not exist. All right, looking at k, we're going to try direct substitution. If you go ahead and plug in 2 up top, I believe you'll get 28. If you plug in 2 on the bottom, you get 0. Okay, so we're dealing with a vertical asymptote at 2, okay, kind of similar to the previous example we just noticed. But if you take a look at it real carefully, notice how we are dealing with a right-sided limit. So if you think about this visually, okay, we know there's a vertical asymptote at 2, but we need to figure out what is the right side doing. And it's either going up or down. All right, so this is when you want to pick a number on the right side of 2, preferably something close to 2, to plug in and kind of see what happens. So maybe we'll go ahead and say we'll test 3. Okay, ideally you'd want to try like 2.1, okay, something close to 2, but you can go ahead and use a whole number. We'll go ahead and try it. Okay, so if we go ahead and plug in 3, 3 squared is 9, times another 3 is 27, plus 21, plus 2. Okay, so if I add all those numbers together, I'm definitely going to get a positive number. If I plug in 3 on the bottom, 9 minus 4 is also positive, and a positive divided by a positive is a positive, so we're going to be going up on the right-hand side. Again, I'm not really concerned with the numbered value because in terms of a vertical asymptote, I'm either going up forever or down forever. I just need to take a look at those signs to help me figure out, is it a positive infinity or a negative infinity? Okay, so we're going we're going up on the right-hand side. The next two examples are pretty similar. Okay, notice how we're dealing with the same function for both. It's just that one of them's from the right-hand side and the other one's from the left. So let's just go ahead and try direct substitution first. Okay, we always start off with that. So if I plug in 3, I'll get 6 plus 5, which is 11. And if I plug in 3 on the bottom, I'll get 0. Okay, so we now know we have another vertical asymptote at 3. So for this example, we want to see what's going on specifically on the right-hand side. Do we go up or do we go down? So you got to test something on the right side of 3, preferably something close to 3, like 3.1. But I would understand if you want to try 4. All right, so if we plug in 4 up top, it's definitely going to be positive. If we plug in 4 on the bottom, definitely going to be positive. Positive divided by positive is positive. So on the right-hand side of this vertical asymptote, we're going up. For the other example, okay, it's the same function and we're approaching the same x value, which we already know has a vertical asymptote. We're now going to figure out what the left-hand side is doing. So maybe we'll test a number to the left of 3, okay, preferably close. Maybe we'll try 2. Okay, 2.9 would be better to test, but I think 2 will work out just fine. So if we plug in 2 up top, that'll be positive. Plug in 2 on the bottom, that'll be negative. Divide those together, we'll get a negative answer. So it looks like on the left-hand side of this vertical asymptote, we're going down. All right, so the last thing I want to go over on page 32 is a different kind of limit that we're going to see much more in future sections, okay, but it is a limit nonetheless, so we could probably talk about it. Okay, so notice how the setup is a little bit different. We have an h approaching 0 this time instead of x approaching a number. And instead of specifically giving us what function we're going to use, okay, it's giving us a format to kind of fill in, knowing that the function is provided over here. All right, so what we're going to do is fill in these different pieces by utilizing this function they give to us. So if we think about this first term here, f of x plus h, okay, notice how that x plus h is representing an input. Okay, just like if there was a number there, you would go ahead and plug it in for those x's. So if we're going to go ahead and plug in x plus h for all those x's, maybe we'll go ahead and write it out just so we can see it. All right, so what I want to do is try to simplify this. Okay, get rid of some of the parentheses, combine some like terms, kind of see what's going to happen. Okay, so if I have x plus h squared, that technically means I have to write it twice and go through a FOIL process. So x times x is x squared, x times h. For the insides, we'll have another x, h, and then h times h will be h squared. Okay, that's just if I expand this quantity being squared. If I continue to work through, I can distribute in the -3, and then I'll just have the +4 on the end. All right, but we still have some parentheses, so maybe we can continue. We'll go ahead and distribute in the 2. All right, and now that all the parentheses are gone, let's see if we have any like terms. And I think the only ones I can see are the 2 xh's kind of in the middle. So 2 plus 2 would give us 4xh. All right, so this is what we kind of have to represent this first piece in the limit. Okay, so let's go ahead and maybe start to fill in what this limit is asking us to do. Okay, so I'm going to copy down limit as h approaches 0. Instead of this f of x plus h portion, I'm going to go ahead and copy down what I kind of found or simplified here. So 2x squared plus 4xh minus 3x minus 3h plus 4. All right, if I continue to look at this, I now have to subtract f of x, which is just representing the original function they gave us. Now, since I'm subtracting the original function, that means I'm subtracting all of it, so we really need to be careful to put it in parentheses. And then the rest of the limit is basically dividing all of that by h. Okay, I know it's a lot, but we're going to see where this kind of takes us. All right, let's go ahead and simplify a little bit more. I can go ahead and distribute in that minus sign. All right, and it's at this point that I'm crossing my fingers that we have a lot of terms that are going to cancel out or at least combine somehow, because I know I have a lot going on here. So let's take a look at some like terms. I notice that I have a positive 2x squared, but over here I have a negative 2x squared, so those will cancel. I notice I have a negative 3x and a positive 3x, so those will cancel. And I also notice I have a positive 4 and a negative 4, so those will cancel. That's so convenient. And actually, that's what's supposed to happen. So it seems like we just have left 4xh minus 3h all over h. Okay, a lot nicer than what we initially started with. All right, so let's go ahead and go through kind of our limit process. Notice how h is approaching 0. So I want to try direct substitution first. If I plug in 0 for the h's, looks like I'll get 0 over 0, okay, which is signifying a whole. So that means we should be able to take this a little bit further with some algebra in order to get our actual limit value. So looking at this, at least in the numerator, they both have an h in common. So we can go ahead and take that out. And that will conveniently cancel with the h that we have on the bottom. So really, we're just left with this 4x minus 3. All right, so now if we tried to plug in 0 for any of the h's, notice how all the h's are gone. So this is actually representing your limit value. I know it's weird because it's not exactly a number like we've been seeing in many of the other examples, but we're going to go ahead and discuss what this actually is representing in a future lesson. Okay, so I guess what I want you to understand, at least at this point, is that sometimes, okay, especially if you're dealing with an h limit, you might not get an actual number as your answer. Okay, it might be an expression, meaning that there's a variable left over.